Let's start. So now we'll have an interesting session on performance issues in PostgreSQL SLRU and how they are optimizing it by Mr. Dilip Kumar. So just some introduction about him. He's also a great PostgreSQL contributor with over 15 years of experience. He is currently working as a principal engineer at EDB, where he has tackled key aspects such as executor, optimizer, storage, parallel query, performance, and scalability with Postgres. So please give it up for Mr. Dilip Kumar.
Yeah, thank you for the introduction. Yeah, so today we are going to discuss on the performance issue in PostgreSQL SLRU, and I will also talk about how we are optimizing it, and we are targeting in PG17. Hope it gets in. So yeah, I'm sure that some of you might not be aware or familiar with the title itself, that what this SLRU is. So I am here to go more into deeper and introduce what it is and what we are talking about. And I just want to cover from the user perspective also, that how user can see this SLRU and how it can cause problem for them. And so that will give you better connection with the SLRU and the internal work what we are doing. So before starting, I just want to know, like, how many of you are internal developer in any database, not specifically PostgreSQL, and how many, and maybe after that we can see who are the user of PostgreSQL. Based on that, we can just tweak the pace of the presentation, and we can just see how much we need to cover and connect from the usability perspective of what things we are talking about. So can we just raise hand that who are aware of like internal of databases and okay, I think and there are quite few audience who is working in internal of the database and they are aware. So I think they can connect very easily that what I am talking about. And then I'll try to cover, or maybe some of the things which is not in my slide, I will try to adjust or add in just to connect from the user perspective also, that how those things are connected from the usability point of view. Okay, so let's go into the agenda. So I think before starting with the introduction of the SLRU, I just want to start with a test. And that test is basically we got from some of our very big customer, where they are running in PostgreSQL in very high load, mostly in the banking application. So I have just replicated that test, and I want to start from that test so that we can connect that what sort of problem we are facing. And after that, I want to, just for going into the detail of SLRU, I just want to connect from the user perspective, like how, where the SLRU come into the picture. For that, we'll little bit understand about the snapshot and tuple visibility, where the MVCC and all these things, I think that is a quite familiar term we might have heard. And then we'll see a cause of the problem in SLRU. So there are basically two things I want to cover. One thing is subtransaction cache overflow, where we are using a lot of subtransactions. And then we'll also connect like the presence of long running transaction, how make it even worse than what it is with the just subtransaction overflow. And then the second problem, which is a lot of uses of multi-xact. And what is multi-xact, that we will discuss by introducing the row locking. And once we are aware of what is multi-xact and how it is getting generated due to row locking, we'll discuss about SLRU, a multi-xact SLRU design. And finally, I want to go into what is SLRU and how it is being used by all these subsystems, where we are talking about the subtransaction cache overflow and multi-xact usage. And then we'll go into the design issue, and I'll try to connect those design issue with the performance test we have seen in the previous slide. And then ultimately, I'll go into different sort of solutions we have tried, and ultimately what solution we are pursuing. And somewhere we are at the verge of commit in 17, maybe in week or two. That is what I hope. But yeah, let's see what exactly happens once it get committed and do not get reverted. That is the ultimate ultimately we can say that it is there in V17. Finally, I'll summarize the whole discussion, and then we can do question and answers. Okay, so this is the first test. So let me a little bit explain about the test. So whoever is connected with the PostgreSQL as a user or as a developer, they might be aware of the PG bench test we generally use in PostgreSQL for performance testing. So I have tweaked this test a bit. Means I'm running in very big server with 128 core machine and 512 GB of RAM and all that. That all things are not a problem, and we are seeing a big scalability in this machine in general with the PG bench test. But I have done some tweak in the test. When the test is running, I tried to create a subtransaction cache overflow. What is subtransaction cache overflow is, for time being, I'll just say a lot of subtransaction within the transaction. And why we are calling cache overflow and all, we'll go later on slides. So I can see the TPS is going very high, almost 30,000 TPS we are seeing in PG bench read write workload. Till 500 seconds, sometime 28,000 to 30,000, some variation is there. Then I created a subtransaction cache overflow, which is just another session which create a lot of subtransaction parallelly and leave a transaction for time being. What happened? Performance dropped to a half. It remained there. You can see from that 545, 700, that is seconds, how long test is running. I haven't put all the data. So you can see for almost 200 seconds, it stays there at the half rate instead of full capacity of 30,000 TPS. Then there's some more twist I added. I created one more transaction, which is long running transaction. So the subtransaction overflow transaction I created, stopped, create and stop. So it will stay for a few seconds and commit. So it is not really a long running transaction. What is long running transaction is, you start a transaction, let it assign a transaction ID by doing some write, like insert, update, anything. Let it assign the transaction ID and leave it for as it. Now you can see the transaction TPS drop is up to 200. From 30,000 to 200 we have reached. So generally, who is analyzing PostgreSQL problem, they might be aware that whenever we see such a drastic change or whenever we see any performance issue, what we try to see? We try to look into the wait events. I think Amit in his presentation also talk about the wait event improvement and all these things. So we look into the wait events. And what we see, the number in wait events, that shows that whenever we try to see how many backend, what it is doing, the number shows that how many time we have observed that backends are waiting on that particular wait events. So you can see the top two, subtransaction SLRU and subtransaction buffer. Those are on the top. So that will give anybody who is like aware in the PostgreSQL internals, they get the quick idea, okay, this is a problem in the subtransaction SLRU lock contention or buffer level contention. What those contentions are, we will talk in later slide while going into the design of the SLRU. But as of now, that is, I think, sufficient. And how will relate that 86,000, is it high or low? We don't know. What is 86,000? You can compare with the empty wait events. What do you see when empty? Empty means the process are not waiting for anything. It means it is working on CPU. So empty is 2,000, but the subtransaction SLRU 86,000. So now you get relate to 2,000 on CPU versus 86,000 on subtransaction SLRU means your processes are completely blocked. So that gives you the relative idea. Otherwise, absolute number doesn't make any sense, because unless you show that empty value, that is the comparison with the CPU. So that is what happened. That is my initial investigation, where I started my investigation of what happened to SLRU. There are a lot of other people. I will not say I am the first one to detect this problem, but that is where I observe it. In past, lot of example, a lot of people already put many blogs. They have observed such problem. But recently, this problem become more frequent. Earlier, we were avoiding this problem. Somebody says subtransaction cache overflow, this problem is there. We'll say, okay, you might have done some problem in your application. You might have just mistakenly created so many subtransaction, which is not, which PostgreSQL internal developer we assume is violation. We should not be created those many. Means that is, that application is not well written. But recently, I've seen a lot of banking application and all, they are really using it for their use case, and they explain why they're using it. And sometimes it is very difficult to change that application. And they are using those sort of use cases in Oracle and all. So then I realized that that use case we cannot say invalid or not well written in the current era where the machines are really high ends and a lot of transactions we are supporting. So there we have started accepting the problem. In last PGCon, I have given the half of this talk as a presenting as a problem only. That time, still that we did not figure out the solution. So here we are in that post presentation only. We talk with some of the hackers, Robert Haas, I think people are aware. Then there we try to identify a solution. And this whole year I worked on this solution, and then I'm going to talk about solution also here in this talk. Okay, so this slide is just to connect that how the test is connected to the SLRU, the SLRU things what we are trying to optimize. First, you need to understand where it come into picture, right? What is the SLRU? So snapshot and tuple visibility, just a brief introduction of MVCC before going into snapshot and tuple visibility. So I think you might have heard that the terms about the isolation level in database, right? Suppose you are running any query, okay, what tuple it will throw you out? You say select star from the table. What tuple it will give you out? That depends upon some factor, right? Suppose I say I have read committed isolation level, I should see only the committed data. Fine, very simple that you just run the query, read the block, whatever is committed, you just throw it out. But is that correct? Is that correct from the isolation perspective or the consistency perspective? Because a transaction can be very long. When you started a query, you read the block by block pages. Suppose you do sequence scan. You're reading some block, some transaction is running concurrently, not committed. You'll say, okay, I'll not read that data. You go the next block. Meanwhile, the transaction got committed. Okay, it is committed. I'm read committed isolation. I should spill out that data. I'll throw the data to user. But it is not consistent view of any transaction. You are seeing the half transaction. So there come into the picture of snapshot isolation, where when the query start, we decide our view. We take a decision what we will see in that query and what we will not see in that query, irrespective of what get committed during my run of the query. So there come into the picture of the snapshot. So I'll not go much into detail of that snapshot, but yeah, in short, we will see what all concurrently running to us, and we will take one view. You can say xmin and xmax boundary that I'll find the smallest transaction running. Okay, and the smaller than this particular transaction, no transaction is smaller than this particular transaction is running. That is I call xmin. So any transaction I see in the pages or any tuple I see in the pages which is inserted by those transactions, I'll assume that as a committed, because that was the smallest transaction running in my system when I saw or I started my query. And then the last transaction committed, that is I set as a max boundary. The maximum number of the serial number, direct transaction number, the maximum number of transaction like 600 or 700, that was the maximum transaction ID was committed in my system. Anything commit beyond that, that will be not in prior to the history. That will be in future for me. So I don't want to see the data for that transaction. So that is the boundary, xmin and xmax boundary for the transaction. In between is my problem where the snapshot comes, because in between some transactions are committed, some are not committed. But those can be alternative or any order. They are not. I cannot keep a bound on them. Xmin and xmax is a bound that below that is committed and after that is not committed. But in between, I need to remember which is parallel to me, which is not parallel to me. So that time I'll just see all the running transactions in the backend. Whichever transaction is running, I'll note down their XIDs and say this is my snapshot. Any tuple committed by those transactions which is matching in my array of the XID is not committed when I took the snapshot because they were running. Anything which is not in array is not exist for me. It means it was committed. They were not running. All running transactions array I'll maintain as a snapshot. So snapshot is nothing but the transactions which are running currently. When I take a snapshot, that's the snapshot for me. So now that is the transaction ID. but they are sub-transaction ID also. So number of concurrent transaction can only be equal to how many concurrent session can be connected, right? Each session can run one transaction, but they can run internally multiple sub-transaction also. So there come a problem because number of sub-transaction within the transaction can be like huge number, right? So I don't want to keep a snapshot so big that the what do you say, the memory footprint of the snapshot is very huge, that I don't want to create that. So what we create is we maintain a max limit of how many sub-transaction each transaction can keep. So in each backend, there's a cache of sub-transaction. If I create up to 64 transaction, I will remember those sub-transaction ID also. So my snapshot is now have the XID array and the sub-transaction ID array. And any tuple which is got committed by either sub-transaction ID or XID, I can just look into that array and find out whether it is concurrent to me or it is in past or in the future. Based on that, I'll take a visibility decision. Just go to next slide. So this is what I just talk in words is showing in a diagram. That snapshot is just the xmin and xmax boundary, and in between I have xid array and sub xid array. You can see both are kind of same array only, but why we'll maintain a separate array, I'll just talk about them later. We could have maintained a single array also, but because of that overflow problem, which I'm going to talk, we'll see why there are two arrays. So now, how the heap page look like? If someone is not aware of that, in PostgreSQL, each tuple maintain a xmin and xmax. Xmin is the xid of a creator of that tuple, that who have inserted that tuple, and xmax is the xid of the deleter. We may say updater and all this, but I'll just say who created this tuple, who removed this tuple, those two xids. Because updater is also, in short, mark as a delete and insert a new tuple. So it become a combination of insert and delete. So I'll just go in terms of insert and delete. And based on that, we will decide that whether the tuple is visible or not, whether it is inserted, which I can see the transaction and not in my snapshot, and it is not deleted within that range of snapshot. I should not see the deleter. I can see inserter, but I do not see deleter. That tuple is visible to me because it is just inserted for me, not deleted for me. So that is what how we decide whether tuple is visible to me or not. So any questions so far in this? If anybody want me to connect more from higher level and I'm going too much in internal, then also we can discuss.
So just wanted to ask, so
yeah.
Snapshots are based on transactions, or like it's like multiple transaction can be a part of one snapshot?
Okay, so each query, whether it is a query running in the snapshot or it is read-only query, need to take a snapshot to identify that what I am going to view in the system, because I am going to scan the data. So what is the snapshot is just a set of transaction IDs, okay, and xmin and xmax boundary, which will tell me the whatever is in the snapshot, those transactions data I will not see. Okay, if those are inserted, I will not see. Those transactions are concurrent to me. Before xmin, those transactions are committed for me. Beyond xmax are never existed for me. They are future transactions. In between, whatever transaction ID are noted are concurrent to me. So those are transactions I will assume that those are not committed for me. That's the only view of snapshot. And each data in the pages contain those XID. And from those, there I'll pick the XID and I'll match into snapshot and find out whether I need to see those tuple or not. That is just the concept of snapshot. Anything else? Okay. Okay, so what is subtransaction cache overflow? So in last slide, we talked that each backend keep a cache of 64 subtransactions. Fine. So a snapshot can contain the transaction ID, contain the subtransaction ID, and for visibility check, we will match into those array and find out whether the transaction is visible to me or not. Subtransaction cache overflow is if some transaction need to create more than 64 transactions, subtransaction, that we cannot maintain into the cache. So what is the problem? Problem is that the whole decision of visibility depends upon the snapshot and the XID array into the snapshot and sub XID array. But if some of the sub XID are lost those are not present in the array because the backend cache for each subtransaction ID itself is lost, because this is only 64 subtransaction, but cache, but we are creating more than that. So we lose those data. So now subtransaction, the snapshot is called incomplete snapshot. So incomplete in a way that XID array is complete, because we know all the XIDs which were running concurrent to me, but sub XID array information is incomplete. So if sub XID array is incomplete, or in such cases, the backend knows that I have overflowed subtransaction cache. So when you read the data or subtransaction data from such backend, we will mark our snapshot as incomplete. Incomplete means we will not store the subtransaction data. It doesn't make any sense to store those data because we cannot rely on the data. Half data doesn't make sense. So now what we have is, we have XID data, those are complete. We do not maintain the sub XID data because there is no point on rely on those data. So there we have so there is the SLRU come into the picture, that each subtransaction ID to parent transaction ID, we maintain a mapping in the disk. Okay. So in the disk pages, we maintain a subtransaction ID to parent transaction ID mapping. What is the use of subtransaction ID to parent transaction ID mapping? Because you know that your XID array is complete, your sub XID array is not complete. But if you find from sub XID to XID that this sub XID belong to this XID, then you can check the visibility check into the XID array. No need to, we don't have sub XID array now, we only have XID array. So if you find the mapping from child to parent and get the XID, you can look the visibility into that, and now your snapshot is again, you get the complete view of the snapshot. Because if XID, top XID is visible, then only subtransaction ID is visible. That is because subtransaction ID child of the top transaction ID. So there what the PG subtransaction SLRU come into picture. I still did not go into detail that what happened in PG subtrans SLRU or any sort of SLRU, what sort of data we maintain into the disk, but I'll go into more detail when I come to the design of the SLRU. So next is what happened in presence of long-running transaction. How long-running transaction put more impact. So what we understood is in previous slide that we do not have complete snapshot. So we need to get a mapping of child to parent, subtransaction ID to XID mapping from a disk. So that is costly. Of course, we know that if you want to get a mapping from somewhere from disk, then it is costly. But how it becomes worse in presence of long-running transaction. So in the first slide, we discussed that what is a snapshot is. Snapshot is the bounded array of XIDs between the XMIN and XMAX. XMIN is the oldest transaction ID which is running. So if you are saying long-running transaction ID, means the oldest transaction ID go very old in past, right? So if oldest transaction ID go very old in past, the range of XID between that oldest XID and current XID become very big, right? It means the tuple got inserted or got updated between those big timestamp all become victim of this incomplete snapshot. All these XIDs need to be looked into the disk to get the parent mapping. So if more number of transactions you need to look into that SLRU, the more problem come about. First thing is that more fetches you do from the SLRU. But there is SLRU is also not completely a disk. It is a disk and cache-based architecture, and cache is smaller on that SLRU also. So if you have more range of XID you look into that, it means more pages from disk to cache need to become, and a lot of frequent buffer eviction happens. Those part I'll cover in part of the while discussing the problem with the SLRU. So this is about the impact of the long-running transaction that make a snapshot wider. So more transactions ID you need to look into the SLRU. That is what so far we learned. Now the next problem, the multi-xact. Anybody who is like using the PostgreSQL or have heard about the multi-xact ID and just heard a term multi-xact ID? Or any problems you have seen related to multi-xact ID? I think maybe not much. Okay. So we'll just discuss what sort of test it is. I don't go in this detail of this test because there's a lot of various way that you can create a multi-xact ID in PostgreSQL. But this is one example that if you take a lock in the main transaction on the row and try to update into a subtransaction, why somebody will try to do this kind of test? Because what happens is that in main, the first they want to ensure that when they want to have multiple rows and they want to acquire the lock on all the rows, and once they get the lock on all the rows, then they want to update it. They don't want to update one row and then in one table it's successful, then second row it is failure, then a lot of rollbacks and all come into picture, or create a lot of this operation into each individual sub transaction. Instead of that, in main transaction I take a row lock on all the multiple tables row, and then when I guarantee that I got the row lock and the update is guaranteed, then I'll go for the update. So that is what this test is trying to achieve. So in this case, we created some sort of multi-xact ID, which I will understand when we are explaining the row locking concept. But if you see the here, I'm more interested into showing the performance data. That what happened when we are creating a lot, when we are running this test with the high load of concurrently 128 clients from using the PG bench infrastructure. So we are fine. We are seeing a good performance. A lot of multi-xact is getting created. I'm not seeing a lot of issues with that because those multi-xact are getting cleaned up also because of vacuum and all. But as soon as we start a long-running transaction, you might be aware that long-running transaction, when we start a vacuum, stop cleaning up because vacuum get blocked because those data could be visible to some of the concurrent select query or any other transaction. So in that case, the multi-xact cleanup stops. And that time, the accessing multi-xact is again costly. That part we'll again see in the design of the SLRU. But yeah, that is costly, and you'll see the performance drastically drop down. And what we'll see in the wait event is multi-xact offset SLRU and multi-xact offset buffer. Those again are two SLRU related wait events or lock. And you see compared to CPU, wait event is very, very high, like just 1400 versus 16,000. So you can see your system is completely operating on or waiting on this log instead of really working on the CPU. Okay, so what's the row locking? This we require to understand when the multi-xact is created in the PostgreSQL. So regular select statement do not give enough protection against concurrent data changes. Suppose you want to read certain data, and based on that read, you want to take a decision that is certain match certain criteria, or you want to do some processing in your application, and after that you want to do the update. But once you have analyzed that okay, it is matching your criteria, and you have done some operation in application, it go to update. By that time, data is changed. Someone else have updated the data. So for those purpose, a row locking come into picture. You select for share or select for update so that concurrently nobody modifies your data. So different sort of protection is there, like select for update. It means you are taking exclusive lock on the row. Nobody can take select for share lock concurrently when you have the select for update lock. So that is required if you want to update a row, but before that you want to select and verify certain constraint offline or not in the database in the application layer, and then you want to update. So there we come, we provide a select for update, and select for share is also there. Like suppose you verify something into a primary key table and you want to insert into foreign key table. It should not happen that while inserting into foreign key table, somebody deleted the row from the primary key table. So that transaction will fail. You don't want that. So you just, while reading into primary key table, you take a select for share lock. So nobody remove that key or update that key, and then you can insert into the foreign key table. So fine, we have the row locking concept. Everything is good so far. Where the multi-xact come into picture? Why we need to create a multi-xact? It's just row locking. So I think in the subtransaction problem and snapshot and visibility also, we saw that we maintain a xmin and xmax into each tuple. Xmin say the XID of the inserter, Xmax say the XID of deleter. But what we did not discuss is that Xmax also store the XID of the locker. Because if somebody have taken a lock on the tuple, where we store that XID? We store again into the Xmax field only. So what's the problem? Where the multi-xact is coming into picture. So some sort of lock like select for share, multiple transaction can take a select for share lock. So they become a multiple Xmax for the same tuple. But tuple is not updated, so you are not creating a new version of the tuple. Generally, in update, we delete the old version and create a new version. Means we mark old version deleted and create a new version. But here we are just taking a lock that we want the two transactions want that nobody should update concurrently. Fine, they are allowed to take that guarantee that nobody should update concurrently. So they can both take a select for share lock. It means they need to be two Xmax, but we have only place for the one Xmax. So they come into the multi-xact. Multi-xact come into the picture that you take those two XID, club them, store it somewhere out, something external storage, or you can say in our terms, we call it as a SLRU. And for that combination of XID, we assign a new ID, a new series of XID, not the, it is not matching with the current XID. You can say start with the multi-xact number 1, 1, 2, 3, 4. One multi-xact can contain 2 XID, 5 XID, 10 XID, 100 XID. So based on that, we create a multi-xact ID, and in Xmax field, we store a multi-xact. Okay, instead of storing the XID, because there's only one place for the XID. So now, again, the problem of SLRU come into picture because we have stored the multi-xact ID into the tuple. And if you want to see the visibility of the tuple, multi-xact cannot give you any idea about that, because all the operations and transaction lifetime, everything is based on the XID. So from multi-xact ID, you need to go again to the SLRU or wherever we are storing that multi-xact ID and fetch what XIDs are there under that multi-xact ID and check the visibility of all those XIDs. So the one problem we have discussed that in multi-xact ID, it is not fixed that how many XIDs can be under one multi-xact ID. It can be any number. One multi-xact ID can contain 10 XID, 2 XID, or 100 of XIDs. There is not fixed limit on that, right? So in the PG subtrans, there is a fixed rule that each XID have the parent XID. So we can keep a 4-byte XID space for each transaction ID. But multi-xact ID, it is variable size. So instead of keeping a 1 SLRU, we maintain a 2 SLRU. That first SLRU will maintain a offset for each XID. So for each multi-xact ID, you can direct access that particular offset. And from there, you can get the starting pointer of the multi-xact ID, and you can fetch all the multi-xact ID by the starting pointer and the length. So this is how the multi-xact is there. The first thing is the offset SLRU, where you have the fixed 4-byte field for each multi-xact ID. So this is direct access. Once you get the direct access from this offset, you can get a starting pointer or starting offset into multi-xact member SLRU and the length, that how many XIDs are there under that particular SLRU, and you can fetch all those XIDs and do the visibility check and all. Okay, so now we have discussed slightly touch upon the SLRU concept and all. Let's discuss what this SLRU is and how we are storing those data. So we are always saying that when we go to SLRU, we are accessing the disk. So we have the disk pages, which maintain those sort of information, like we just talked that multi-xact ID to XID mapping, the subtransaction ID to the top transaction ID mapping. All these mapping are contained on these pages. Above this page, we have one cache also, which is LRU based a buffer cache. And the name SLRU come from because it is very simple LRU victim buffer selection mechanism it is using. So we are calling it SLRU. So in short term, that SLRU provide a storage management for buffer access for all the transaction related data. Like we just talk about PG subtrans, there is a multi-xact ID, there is a PG-xact for maintaining the transaction commit status. All these transaction related data we maintain into those SLRU pages, which is backed by a buffer cache. So you don't need to directly access the cache. And then for accessing those buffer into that cache, you have a control lock, a centralized control lock. So that also become a problem for one part of problem, that you need to access, take that lock for accessing any sort of pages. And then each slot in the buffer is containing a buffer lock just to do the IO with the disk. So what is the design issue with this particular architecture? So three main issues we identified while analyzing those two problems in the past. So problem one is frequent SLRU buffer eviction. So you remember, like we discussed about what happened particularly when there's a long-running transaction. When there was long-running transaction, we told that range of the snapshot is very, very huge. It means number of XIDs we need to look into the SLRU is also increased. If number of XID range increase, it means number of pages, we are going to access more number of pages. It means number of hot pages, if you are keeping into disk, they are going to frequently evict out because the cache is limited size. Suppose 32 pages are there, but you are accessing 100 pages. It means whatever is there in cache, that will not be going into the cache, not going to remain into the cache. So that is the topmost problem we have identified, where the eviction is too frequent because of the range of the XIDs what you are accessing is big. The second problem is, so even though the long running transaction is not there, we have seen that performance drop almost a half. And that is not because of that eviction is frequent, because in general, what XID range you are accessing is not very big if there is no long running transaction. So even though the short range of transaction ID you are accessing, mostly you'll find those XIDs into the cache. But problem is you need to still take a control lock on that SLRU buffer cache before accessing it. Although that cache, the lock is read lock, but somebody have to write this data also, subtransactions data into the cache also somebody have to write. So the writer and reader sort of contention is there that create the second problem, that contention on the first lock we are seeing subtrans SLRU lock. The next problem, last problem. Like somebody asked me that you have created a subtransaction overflow once and kept that transaction open. It means we have written the data into the cache of subtransaction cache. And then only readers are there which is reading the data. So what is the problem? Means now all are taking a read lock. There should not be any contention. But there we have analyzed further that this particular case, it was not showing even in the wait event because there is no waiting on the lock. It is because of frequently whenever we acquire a lock, we need to modify the lock variable, right, internally. So that variable, that again lock is shared. So across the multiple processes accessing, that share variable is getting modified. And when you need to read that variable, your cache is older and the CPU cache is frequently getting evicted. And at that level, the third problem is coming. So not only the lock, but centralized variable is also a problem in this particular case when only readers are there. Okay, now let's go into the solution era, that what solution we have tried in PostgreSQL and what performance number we have seen. So any problem in what problems are there? Any question is related to that?
I didn't understand the third problem. Can you explain again?
The third problem, right?
Yeah.
Okay. So second problem, we told that there's a lock contention, reader and writer is contending on that lock. So that part is clear. So somebody asked me a question that if I have written all the data into the cache, because once I created overflow, I am holding that transaction. It means writer process have done its job. So now all are reading the data. They are just taking a share lock. So why there is a problem, right? That is exactly the question. The thing is, for taking a lock also, you need to modify that lock variable. Maybe if you take understand a simple mutex kind of lock, where you make 0 to 1. 1 means I have locked, 0 means I have released the lock. And that is share variable. I make it 0 to 1. Other process want to check whether it is 0 or 1, whether I can take a lock or not, right? It's for reading that variable, its data was 0 earlier. Now that cache variable modified by other CPU process. So need that CPU this CPU's cache is older. It need to fetch from somewhere, RAM or somewhere. So other CPU will flush that data to RAM and we will read it. So CPU's cache is getting frequently invalidated. So that is the third problem is about. Any other question? Okay, let's go into the solution space and first think the solution for the first problem. The first problem is that frequent buffer eviction is there, that your cache is smaller, and if you are accessing a large number of transaction ID, you are loading a lot of disk pages. You need to evict out the pages from the cache very frequently. Okay, very simple solution. You just increase the cache size. What's the problem? Because currently SLRU cache is very small. So problem is this one, which is a second bullet point. For the sub bullet point is written that all the operation basically in cache, the search, because the cache is designed so small, the search is sequence. And second thing is the victim buffer selection have to be sequential because you need to find whichever is the oldest or least recently used buffer. That only we need to evict out. We cannot evict out any page. So victim buffer, even though you make a cache very big, the victim buffer eviction become a very, very slow process. So again, it will, whatever you gain, you lose. Second idea, somebody suggested, okay, we can make a hash table, buffer mapping hash table. So at least whoever is looking up for the buffer, that can be a direct access instead of sequences first. Fine. And then we can increase the cache size because now cache size is bigger, fine, but searching is at least faster, that you can direct access to that page, that which buffer is holding your page, or it do not hold the pages. It works, but it has some certain other problem, that still the eviction, searching is faster because of hash, but victim buffer eviction is still a slow process because you need to find the least recently used again by the sequencers. So that also doesn't solve the problem completely, although it helped a lot. So that was my first approach where we implemented this. Now let's come to the third approach, which we are trying currently in the PostgreSQL and hoping it to get committed. Let's use these two use, but yeah, let's use the partially associative cache. So instead of assuming that full cache is fully associative cache, let's assume a partial associative cache where we divide the cache into pieces. Okay, let's take, so you want to increase the cache size, but you don't want to search in whole cache for victim buffer selection. Let's make cache a partially associative. So keep the whatever currently eviction is faster, but cache is small. Keep the cache size same, but take a multiple cache of that same size. So suppose cache is having only 16 buffer, where you think that sequence search is pretty fast in modern CPUs. So keep a 16 buffer size only for victim buffer selection, but take hundreds of such 16 buffer size. So we are making the buffer size configurable based on your workload, but the cache size at the small granular level, a single cache is of same size, but there will be multiple caches of that same size. So all search, each page have its fixed destination within only that cache. It cannot go into any cache. That cache we call a small cache as a bank, buffer bank. So each page can go into that particular buffer bank. So there's a problem. There's a question that that now the each page, instead of having a complete range of the buffer pool where you have suppose 100 buffers in a cache, and the victim buffer selection should be actually least recently used, but you are not finding the least recently used in the 100 buffer. Instead of, you're just finding the least recently used within the 16 buffer. Isn't that a problem, that you are evicting out something which is not really least recently used, but it's just a relatively least recently used within those 16 buffer? Yeah, that is a problem. But what we have seen is that it's particular SLRU use case, that doesn't matter. That is not the finding almost least recently used is not that much of a problem, and our goal is not to find the exactly least recently used, but reducing the contention on the lock and increasing the cache size, and by not paying the cost of sequence searching into that. So that is a solution what we think is working best, at least for the first problem. Now go into the second and third problem. We are saying that high contention on centralized lock and frequent CPU cache misses. So there also, the first idea what came into picture is that instead of having a single lock, if we provide a hash, because hash was the faster for the direct access of the memory, we can provide a partition hash. And each partition can be mapped by a single independent lock, so that your lock contention is also removed. But there again, the problem come about the eviction remain the same problem. That if you keep a same big buffer pool, the eviction is the same problem here also. So again, we continue the idea of the partially associative cache for the second problem also. And since you have divided the cache, whole cache into a different bank, why don't we invent a bank-wise lock? Because you are doing eviction into the bank, you are searching into the bank. Why we need a control lock? We can have a just bank-wise lock. So that bank-wise lock have solved both second and third problem. So first thing is the contention of the lock is gone because you don't have one centralized lock. If you have multiple number of banks, you have a lock for each bank. And the last problem where we are saying that we are modified a common variable, whether it is a lock variable or the LRU variable, which I did not go into much detail, but yeah. So those variables also we are maintaining at the bank level. So lock is at bank level, the LRU victim buffer search is at the bank level. So LRU variable, which is tracking, which is the least recently used buffer, is also at the bank level. So all this problem is now not global, all are local to the each associative cache. So with that, what we have seen, the performance number. So the same test what we have repeated with the subtransaction in the first slide, where we are seeing that with the subtransaction overflow, the performance dropped to the half level. Okay, and after having the solution of first thing is just the SLRU bank that we divided cache into a different buffer bank. We have gained a slightly, you can see the red line just touching above surface of the blue line. That is not huge, but when we divided the bank or divided a bank-wise lock, then we can see a huge gain. Almost it reached to the performance level. As such, there is no subtransaction overflow. We have gained original performance even with the subtransaction overflow is same as the, like if you don't create any subtransaction overflow. And the second performance is with the multi-xact script. So this test also I am repeating the same test where we are creating a lot of multi-xact and also running a long running transaction concurrently, which I'm saying here in short LRT. So you see the three performance number on head. After a certain client, if you see that after 30, it is completely dropping down very fast. And if you implement only SLRU bank, so with that, we are actually increasing the cache size. That is why we are seeing the gain. And we are dividing into multiple caches. So you are seeing a certain gain of the performance. And the further when we implement a bank-wise lock, you can see gain is much more than what we are seeing at just dividing into the bank. So this is summary of our talk. Like we have seen the subtransaction overflow problem and the multi-xact problem when using the row locking, and high rate of multi-xact generation is called the contention on the multi-xact SLRU. In SLRU design, we have mainly identified three problems like frequent buffer eviction, the contention of the SLRU lock, and frequent CPU cache miss because of the common global variable are getting modified. And for optimization, finally, we have selected to divide the bank into partially associative cache, and then also implement per cache-wise LRU counter and the lock. Okay, any question in? Yes.
Guys, before we have the questions, can we please have a huge round of applause for Dilip? Yeah, now we can take up any questions. Please don't hesitate to ask. This is a good platform for.
Hey Dilip, this is Archit. So the change that you've made in buffer pool is specific only for SLRU specific transactions.
It's SLRU specific.
Exactly. So given that it boosts performance, why not extend the same solution for all the queries in general in the buffer pool?
In general buffer pool.
Yes.
Yeah,
Because
actually.
that is how MySQL buffer pool generally is. We have different hot regions, cold regions, and the eviction happens specifically from the cold regions.
Okay. Yeah, very good question. Actually, first solution what we tried and which I did not discuss here is like using a shared buffer pool first for the SLRU also, and then optimize it in a way that it can improve the performance for in general queries also, and for the SLRU specific, like transaction specific data also. But the for making that work progress in PostgreSQL, I think sometimes we need to be instead of making a generic solution, you need to go to the specific solution. Reason is that if you try to put so much of optimization, so many optimizations in a common buffer pool, it can be eventual process over the period of time, but in one shot you cannot get that patch in it. You have to go in multiple parts. So that is, you can say somewhere the way of operating in PostgreSQL also, that if you work on something specific, it is easy to solve that problem instead of solving all the problem together. So that is the one reason.
Okay. So I have a basic question. Sorry if it's dumb.
Yeah.
Of the MECC architecture. Let's say transactions, I'm guessing the transaction IDs are generated in a monotonous manner. Now I have 4, 5, 6 going on. 4 is done, 4 is committed, and 5 is a long-running transaction, but 6 is done, 6 is committed. Now, won't my order get screwed up? Because let's say if a new transaction starts, I can't say you can see everything before 6 because 5 is still running. Sort of like a head of line blocking issue. How is it addressed in Postgres?
Okay, so I'll just repeat your question only. So it is just about the understanding of snapshots xmin and xmax, right? So suppose a transaction ID 4 is committed, 5 is running, 6 is done, and maybe 7 is running and 8 is committed. Okay, let's take example. So xmin is the oldest running transaction ID. Okay, so if you see all the backend, somewhere 5 is running. Okay, so when you inspect each backend or each session, you'll find a 5 as a running transaction. Okay, and the 8 is the committed transaction. So 5 is the oldest running XID because there is no smaller than 5 which is running. 4 is committed. There is 3 is committed long backend. No backend is holding anything smaller than 5 which is running. So 5 is xmin. So anything smaller than 5 I will assume as a committed. 8. Suppose 8 is the latest committed XID. I'll assume beyond 8 everything is running for me. In between I will hold the XID. In between, what is between 5 and 8 is 6. 6 was running. So I'll hold the 6. I'll hold the 5. The 5 and 6 is there in my snapshot. 7 is suppose committed is not in my snapshot. So now you want to see the visibility check. You will how the visibility check come into picture is you will just while doing the scan, suppose sequence scan, you'll find a tuple inserted by XID 10. You'll just come into 10. Is 10 below xmin? 4? No. Beyond xmax? Yes. 8. It means 10 is running for me. I don't want to see the data of 10. I cannot see the data of 10. If anything come 3, okay, 3 is beyond 5. So 3 is visible to me. I'll assume that 3 is data I can directly read. Anything come 5, 6, 7, 8, those are beyond the between the boundary. So I need to map into the array. So when I try to see the 6, search the 6, I'll find the 6 is there. I'll find the 5, 5 is there. It means those are running for me. I cannot see their data. And whichever is 7, I will not find into that array because it was committed. No backend is running those data while taking the snapshot. It means I will not find into the 7 that array. So 7 is committed for me.
Okay. So basically it's not based on greater than, less than check, but checking and comparing.
Yes. So boundaries are greater than, less than, in between data are matching based.
Yeah, got it.
Any more question?
Yep. Thanks for the amazing talk. Firstly, yeah. Are you by any chance aware of MGLRU?
Which one?
MGLRU.
MGLRU.
Yeah.
No.
So actually, kernel adopted this paging. Kernel also has their own page eviction and all this thing, right? So they have recently, like, they've been experimenting with MGLRU, and it turns out exactly the same. Like, so even when we were discussing, like, why not adopt it to like common scenarios, I think it'll work really nice, because if kernel is able to handle journal workloads on MJLRU, it should, I think, work for like all
Right.
the Postgres common.
Yes, so I think that is very good observation. When I started evaluating this problem, I thought of a lot of different algorithm first to which sort of LRU we can consider. I wrote a POC for LFU also, and other LRU which is usage based count, like if you see in the shared buffer pool of PostgreSQL. Then I realized after experiment that LRU is not a problem. The LRU eviction algorithm is not a problem for this particular case. In this particular case, a problem is the locking and the way we are handling it. So finally, instead of best LRU algorithm, we went to the suboptimal LRU algorithm, because we have divided into partially associative cache, which is not actually a best LRU algorithm. We will not find the least recently used, actual least recently used, but still we are performing way better, because here the LRU algorithm is not a problem. The implementation is a problem. Yeah, good question.
Can you go 2 slides back?
Yes, sure.
Yeah. So here I can see that the drop that comes, the number of clients is the same for all of these. Is
the number of client is down 25.
Yeah, between 50 and 75.
Yes, yes.
So is it intended due to a configuration, or
this drop is because of a long running transaction? We are running a long running transaction.
Yeah.
So multi-xact problem we have solved, right? But the long running transaction is causing a vacuum to hold, which is table is getting bloated, and table bloat problem we cannot solve in this particular because of SLRU. So what we have solved is, because of table bloat, a lot of transactions a lot of tuples are having a multi-xact ID, and for visibility, multiple times we are looking into the SLRU. So that problem is solved. But in general, table bloat, which is causing a table to big and a lot of tuple we need to access for any query, that problem cannot be solved with that we have to close the long running transactions. If you close the LRT here, everything will go back to the normal. So this is down is because of LRT.
But I can see that the number of clients are around the same for head, SLRU, banks, and bank-wise log. So is there a particular reason behind there be a vertical line attaching all these drops? Is there a particular reason behind that?
That why it is not making a vertical line?
Yeah, like
because the this particular head, the impact is not only because of the bloat, impact is because of the SLRU contention also. So the head is giving so fast down at the 30 only because of it is hitting the SLRU contention as well. Okay, but in the other case where we have improved the SLRU contention is gone. So now we are hitting the contention only because of the table size got bloated. A number of records got, the old record got increased, the visibility got slow because you have to scan a lot of tuples.
Okay.
Okay, thank you. That is good observation.
Yeah, so I have a question on the same slide.
Yes.
So like we can see that, that like there's a peak, right? So, and as the number of clients increase, the workload is decreasing. So there will be a point where head, SLRU, and bankwise logs will make a merge, right? So the possible solution for us to do is like run head parallelly or run SLRU parallelly, but for a large number of clients, it's still going to cause an issue. So
the thing is that since you include the LRT long running transaction, the more number of the workload increase, the more number of client we add, the contention because of the LRT, not because of the SLRU. Okay, because of this particular after peak you are seeing drop down because of LRT, the number of tuples become too long. So number of tuple become too many because of bloat. We are not cleaning up the old tuple. So if you are doing any scan, the index size is big. The number of pages are big. The IO is more. So the number of more clients you throw to it, they finally going to ultimately become a slower because of the IO become bottleneck, the page log become bottleneck and all these things. So maybe I should have, if you see this particular case, beyond this peak, maybe we shouldn't have shown this as anything related to SLRU. That all because of the impact of the LRT. If you run, remove all the SLRU problem, remove the multi-xact, run the simple PG bench, and run a LRT, you will see the same flat PG bench will dip equally or with the LRT because of the table bloat. And table bloat have a lot of other issues like lock manager problems, the frequent IO and all these things.
Thank you.
Yeah, welcome.
Dilip, so I have one doubt. The tuning what you're doing, this particular tuning what you're doing, is it nothing but so we have, as I know, Postgres have multiple cache. So one is the common buffer cache, and this you're talking about the C-log cache. So you tune the C-log, right?
Yes,
cache,
yes.
right?
This is exactly what you are saying. C-log cache is the SLRU cache which is used by C-log, PG subtrans, multi-xact, notify, serials. Many transaction-related data is getting stored into the SLRU.
This particular cache.
Yes, this particular cache. Okay. So that cache we are optimizing.
Okay, okay. And one more doubt. See, suppose I have a transaction T1. Under the transaction T1, I have multiple sub-transactions, right? Now, how does, when there is coming to the visibility rules, right? I think everyone know visibility rules. So what I mean is when it's come to the visibility of particular, so the sub-transaction one committed some data. When it comes to the tuple level, so how does it apply to the visibility? Like
so if see, when you take a snapshot, okay, at that time, if a top transaction is running, whether irrespective of whether sub-transaction is committed or not, those sub-transactions will be maintained into the cache. So even though commit that sub-transaction, they will not release its slot. It will be there. So when I take a snapshot, I will take that sub-transaction as a running for me, not as a committed for me. Okay, so when you see the visibility, you'll find that sub-transaction into that snapshot and you'll assume it is running because the top transaction was running.
Okay, got it, got it. Got it. Thank you. Thank you.
Do we have any more questions? Okay, so can we please have the goodie for Mr. Dilip as well?
Thank you, everyone. Thank you.
Thank you so much for the talk.